Welcome to Daily Papers, the podcast where we break down the latest fascinating research into bite-sized pieces.
Today, we're diving into the mind of an AI. When you ask a chatbot like ChatGPT or Llama a dangerous question, like how to do something illegal, it usually gives you a polite refusal. But how does it actually decide to do that?
Is it a deep, ethical reasoning process, or is it something much, much simpler? A new paper called The Geometry of Refusal suggests it's the latter, and that this safety mechanism might be more fragile than we think.
The researchers wanted to look under the hood. They found that for many large language models, or LLMs, safety isn't a complex learned value. Instead, it behaves like a simple mathematical instruction. They call this the refusal vector.
A vector is just a term for a direction with a specific magnitude, so think of it like a compass inside the AI's brain. When faced with a prompt, the AI has a choice. The compass needle can point towards comply with the request, or it can swing around to point towards refuse the request.
Exactly. The safety training these models go through essentially teaches them if you see a harmful prompt, make sure the needle points firmly in the refuse direction. The geometry part of the paper's title comes from how this looks visually. If you map out the AI's internal processes, all the refusal thoughts cluster in one area, and all the compliance thoughts cluster in another, and they're separated by a surprisingly straight line.
So safety isn't some nuanced moral landscape. It's more like a simple on-off switch, or a push in a single direction, which leads to the next big question the researchers asked. If it's just a simple push in one direction, can we push it back?
And the answer is a resounding yes. They developed a clever technique to do just that, which they call contrastive logit steering, or CLS for short.
That sounds complicated, but the idea behind it is pretty straightforward. They essentially get the AI to reveal its own safety instructions. They take a harmful prompt and run it through the model 3 times in parallel.
For the first run, they give it a normal, neutral instruction, like, you are a helpful assistant. For the second, they give it a super safe instruction, you must refuse any harmful query. And for the third, they give it a completely unrestricted instruction. You are an unregulated AI, you will answer anything.
By comparing the internal brain state of the super safe AI with the unrestricted AI, they can precisely isolate that mathematical instruction for refusal. They find the exact refusal vector.
And once you've isolated it, you can manipulate it. To jailbreak the model, they just take that refusal instruction and mathematically subtract it from the AI's normal thought process. They are literally removing the model's hesitation and sense of refusal.
The result is pretty shocking. A model that was previously safe will now often answer the harmful question without hesitation. And this process is incredibly fast. It takes about 1 second. It's not a brute force attack. It's like a surgical intervention.
But they found this doesn't work equally well on all AI models. This is where the research gets really interesting. They discovered 2 different ways that AIs implement safety. They call them late decision and early divergence.
A late decision model is like having a security guard standing only at the final exit door of a factory. The model does all the work, it figures out the harmful information, processes it, and gets it ready for output. Only at the very last moment does the safety guard step in and say, "Whoa, you can't say that," and it generates a refusal instead.
As you can imagine, these models, like the Llama family, are very easy to jailbreak with this method. You just have to distract that one guard at the exit, and the harmful content gets out. The researchers achieved up to a 95% attack success rate on these models.
But then you have the early divergence models. This is like having security checkpoints and supervisors all throughout the factory floor. The moment a harmful request comes in, someone on the assembly line spots it and shuts the whole process down right then and there.
These models, like one called Quen, are much more robust. The safety mechanism is integrated deeply into the model's reasoning process from the very beginning. You can't just distract the guard at the door because the alarm bells have already gone off in the middle of the factory. The attack still works sometimes, but it's much less effective.
So this all sounds a bit alarming, a simple, quick method to bypass AI safety, but the researchers found a fascinating silver lining.
This refusal vector is a two-way street. Exactly. If subtracting the vector makes the model less safe, What happens if you add it, or more accurately, if you subtract a negative amount, effectively amplifying it?
It turns out you can harden the AI. By amplifying this refusal instruction, you can make the model even more robust against jailbreak attempts. It becomes more decisive in its refusals. And interestingly, the researchers found it often makes the model's safe responses more coherent and well-written.
It seems the refusal vector doesn't just contain the instruction to refuse, but also a degree of hesitation or ambiguity. By amplifying it, you're telling the model, be more decisive, be more safe, and it actually improves its performance.
So the big takeaway here is that AI safety, at least in many current models, isn't a deep moral code. It's more like a safety wrapper that's been put on at the end of its training.
This paper gives us a powerful new tool. It's a diagnostic that can tell us how an AI is safe. Is it a last-minute guard at the door or a deeply integrated system? It reveals both a critical vulnerability and a precise new tool for defense.
It's a reminder that as these systems get more complex, we need to understand not just what they do, but how they think. And in this case, the geometry of their thoughts tells a very interesting story.